which is our tape lag. So the setup of our experiment and kind of our goal of this experiment today is to find the charge of these two pieces of tape when they're kind of charged with static electricity. So how do we do this? First, we got to charge them. So we cut out these two pieces of tape, stick them together, and then rip them apart really fast. We gingerly take one piece of tape and put it on the bottom book stands that we saw here, and then we take the top piece of tape and then we slowly lower it until the bottom piece of tape starts to bow upward. So there's some characteristics that we had to record here. So the tape length was about 0.1 meter, and it was about 0.002 kilograms in mass. And then the distance between the tapes when the tape started to finally bow upward was about 4.5 centimeters. So how do we use this recorded information to find the charge? Well, first, we kind of got to make some assumptions. So we know that the tape is motion stationary when it bowed upwards at 0.045 centimeters. So the net force is about 0. So that means the force of gravity pulling the tape downward and the electric force pulling the tape upward have to cancel out. So we can find the force due to gravity by multiplying its mass times the acceleration due to gravity, and we get negative 0.00196 newtons. Then we do the exact same thing with the electric force and we find the electric force. So how do we do this? Well, we first find the electric field expelled by the top piece of tape, which is the Coulomb's constant, the 9 times 10 to the 9, times the charge of this top piece of tape, divided by the distance between the two pieces of tape squared. And then this is the r hat vector, but right now I'm just considering it as magnitude and not dealing with the vectors because it's all in one direction, the y direction. Then once you have the electric field, you can find the electric force by multiplying the charge of the bottom piece of tape by the electric field. And we're assuming that the way that we charge the tapes, that the charges are equal and opposite. And when you plug this all together, you get that the charge is about 2.1 times e to the times 10 to the negative 8 coulombs. So then you can also do this computationally. You can see the results of our computation right here, but how we did this is we initiate our constants, we initiate our tape parameters, and then we plug in our charge guesses here. Then we initiate our bottom tape and our top tape, and with all of this information initiated, we can use this electric field function to find our electric field. Then we can do our force calculations to find our net force, and we want to plug in charges until this net force is about 0. As you can see here, our net force isn't perfectly 0 when we use the net force we found previously, but it's very, very close. And the issue is that I rounded in my previous calculations, but the computer doesn't round and is far more accurate. But obviously our hand calculations is pretty decent. So kind of what can we discuss from this experiment? Obviously, we got our answer about what is the charge of one piece of tape, and it's about 2.1 times 10 to the negative 8 coulombs. Then some other assumptions we made to make our calculations and make our computational model is that we're obviously going to ignore air resistance because the only two forces acting on the piece of tape is the electric and gravitational force. We're treating that long tape as a point charge in our calculations to make things simpler. And we also assume the bowing of the tape is gonna still keep kind of the same amount of charge evenly distributed, so we can kind of keep with our point charge calculations. Then what other discussion can we make? We can kind of consider about kind of the electrons and protons making this phenomenon possible. What if they flipped signs? So what if electrons were positive and protons are negative? And I believe that even if the signs of the particles are flipped, the tape still exhibits the same phenomenon. The tape would still be attracted together. There would still be a particle that has a electric field that is radially inward and another particle that has an electric field that is radially outward, and the tape would still move up and be attracted to each other. So I don't think the changing of the particle signs are going to affect our observations. And then you can also consider why it is important to do the experiment as the way we did. Why is it important that we gingerly put the tape on the books? Why is it important that our skin only minimally interacts with the tape? And that's because skin can interact with static electricity too. If your skin is touching the tape too much, it can donate electrons and then reset the tape to a neutral charge. And if the tape is now neutral again, it won't experience an electrical force, and so the phenomenon we observed wouldn't happen. Thank you.